In Practical Exercise 5, we continue to develop our understanding of biological signal detection and amplification through a construction of an EMG circuit that will utilize minute muscular depolarization in our muscles to light up an LED. Nerve cells, known as motor neurons, transmit electrical signals that cause muscles to contract or relax. EMG is an electrodiagnostic medicine technique for evaluating and recording the electrical activity produced by motor neurons in skeletal muscles. The voltages which muscles generate is usually around 100 millivolts when contracted and is greatly attenuated by internal tissue and skin, so it's very weak, but it can't be measured at the surface of the skin. EMG signals contain frequencies ranging from 10 Hz or lower up to 1000 Hz or higher, but we want to avoid 50 Hz because of artifacts of the electronics in the room.
To observe EMG signals, we built a differential amplifier with high common mode rejection ratio, which rejects global signals by looking at the difference in voltage between two nearby points on the skin. We connected two electrodes on the muscle we wanted to examine about 1 to 2 centimeters from each other, and a third electrode, a reference one, to the ground, which was connected to the elbow. Now we want to use an instrumentation amplifier which draws almost zero current from the input leads, because otherwise the usefulness of the electrodes can degrade. Next, we built a second-order active filter to provide a roll-off of 40 decibels per decade, and because unfiltered EMG picks up a large amount of noise, we want to construct this filter without any gain. So after the filtration, we have a non-inverting amplification circuit that takes care of that. For our pre-amplification circuit, we used a INA 118 instrumentation amplifier with a gain resistor of 5.6k ohms to get a total gain of approximately 10, so we don't amplify the noise too much. The equation for the gain is derived from the two central 25k resistors connected to the gain resistor downstream.
We made our second-order bandpass by combining a second-order high-pass and a low-pass filter with a LM324N operational amplifier, where the second-order low or high pass cut off frequency and can be calculated by this equation. The resistors and capacitors will be equal within both filters, since we still don't want to amplify any noise. Then at the end of the circuit, we had the non-inverting amplification and an LED, where we calculated the gain within this equation. To start off, we had our frequency with the range of 50 to 500 Hz and gain of 501, but figured out through trial and error that for the bicep muscle, 103 to 498 Hz with a gain of 1001 worked better for all of us. For Arnar's calf muscle, frequencies from 150 to 498 Hz and a gain of 1001 worked the best. For Helga's cheek muscle, we used a gain of 1001 and frequencies from 0.58 to 498 Hz, which was interesting because the range includes 50 Hz, but the range worked very well for the chin, as you can see in the video.